Alright, so let's look at more interesting sequential circuits. We've done a D latch, but let's look at an edge triggered device now. Suppose we want an edge triggered D flip-flop. So the behavior we want is something like this. On the falling edge of our clock, we want our input to get loaded into our device and to appear on our output. And we can make this out of 3 cells as follows. Our cell on the west will just be our usual feedback cell, as will our cell on the east, which will also send a bit out as our flip-flop's output. The middle cell is where all the action happens, and the clock is going to come in on the top and D is going to come in on the bottom. And so the way we're going to look at this is in 2 pictures. If we have a 1 coming in the top, we want our cell to do the following. We want to take the D input from the south, send that to the west, but recirculate what's coming in from the east. So when the clock is 1, our Q bit is stable. We can change our D input and Q is not affected. On the other hand, when our clock is a 0, and we have a 0 coming in on the top, we want to take the value from the west and send that over to the east and also recirculate it back to the west. So let me redraw these cells just for clarity. They don't change based on the clock, obviously, but to help see what's going on. And we still have a D coming in on the bottom. So what's the expected behavior here? If D is coming in on the bottom and the clock is 0, D is ignored, and you have a bit circulating through this leftmost cell, coming into the middle cell and going back. So your bit is trapped in here. This is the slave component, and it's also being copied over here. Now this cell on the right, part of the master side, is transmitting that to the Q output of the flip-flop, but it's also recirculating it back. The recirculating doesn't do anything. It just sort of presents the bit at the input of this cell. But when the clock changes to 1, 2 things happen. 1, this cell begins circulating what's coming in from the east, and so this bit value, which was what we were seeing for Q, is now trapped between these 2 stages. At the same time, the D input starts moving over to the left cell and is now coming into here, and again it's being sent back in, but it's not going anywhere. It's just appearing on the inputs of this middle cell. But now when the clock drops, the value that's coming out here, which was the D value at the time the clock dropped, is now trapped in here and sent out. So it's a basic master-slave arrangement being used to create an edge-triggered device, in this case an edge-triggered D flip-flop. And again, this is an example where we could build this out of 2 D latches hooked together, each with a pair of cross-coupled inverting gates, and hook those in a master-slave setup with a clock and the complement of the clock controlling the movement from one stage to the next. We could do that, but here we're basically doing our entire circuit with 3 cells. And again, the only thing that's really specific to this is this cell right here. We're not using the output here or here. We could send Q to the north, for example, and we could create an entire second flip-flop using this as the leftmost stage. So we'd be doing asymptotically 2 cells per flip-flop bit, which is a lot better than we would do making a full-scale standard digital design for a master-slave D flip-flop using discrete components.